So I think all of you can do up to this particular point, right? This is M1, okay? All right.
Yes, sir.
Then now the same thing can be written as M1 d square x1 by dt square is written as d by dt dx by dt. Okay, so which is nothing but d by dt of dx by dt is nothing but v1, no? Velocity, right? Okay, so b1 v1 plus k1 into integral v1 dt plus b2 and so on. Now, up to this point is clear. So, do you have the table with you? Yesterday we did. So, are you trying to write notes or not?
Yes, sir. We have, sir.
Okay, now tell me. Yeah, M1 is equivalent of what?
Inductors, sir. L.
Inductance L1. How we can write d by dt of V1?
D square x1 by dt square.
This d square x1 by dt square is written as what?
d by dt of I.
So V1 is equivalent, velocity is equivalent of what?
Current.
Current. So we can write L1 di1 by dt, okay?
Yes, sir.
The first term. This term. M1 is L1. dv1 by dt is what we can write? D by dt of I1. Correct, no?
Yes, sir.
And plus B1 is equivalent of what?
Resistance, sir.
Resistance.
Resistance R1. And V1 we can write it as
I1.
I1. So V1 we can write it as I1. Right. The next term K1. K1 is written as
1 by C.
1 by C1. And integral of V1 dt is written as
Charge Q.
charge Q, but equivalent.
Integral ID.
Integral I dt.
So we can write it as integral I dt. It's a mess equation, no? So 1 by C1 integral I dt is what?
VC1. VC1.
C1. Correct, no? Right. Plus B2 is equivalent of what?
R2.
R2. So R2 into V1 minus V2 is what?
I1 minus I2.
I1 minus I2. Plus B3 is equivalent of what? R3. V1 minus V3.
I1 minus I2.
So this is what conversion of equation, correct? Mechanical to using mechanical electrical force voltage analogy, right? So now you see M1, so is sharing with K1 and B1, so they are individual, right? But shared elements of what? B2, okay, so B2 3, correct, no? And B3, correct, no? Is it not? Yeah. So how can we write this? So L1 di1 by dt plus R1 I1 plus 1 by C1 integral I1 dt. So this is what the equation we have done right now. Is this clear so far?
Yes, sir.
Yeah. Now, this you are trying to write as node equation, right? So, mesh equation. L1 di1 by dt. So, is what? Voltage across
Inductor.
inductor. R1 I1. R1 I1. Right. So, how many masses are there? Those many mesh equations you will get. So, this is first mesh. Right. R1 I1, L1. So L1 di1 by dt. So this term, right, and then C1, 1 by C1 integral I d1, right. So this is what individual components, and shared components are R2 into I1 minus I2 and R3 into I1 minus I2. Is it fine? Is that fine?
Yes, sir.
So then next this is M2, okay. So this you can write, okay. And similarly, we can write this equation and equivalent now. It is okay.
Yes, sir.
Naga Sharat Chandra, K Naga Sharat Chandra. Now tell me this equivalent K23 into X2 minus, this is what we are getting, no? K23 is equivalent of what? One by C23. C23 means what? It is a capacitance shared between mesh 2 and mesh 3. So this is 1 by C23. Then that means what? This is the capacitance which is shared between second node and third node, right? Yeah. So now I think you can do it, no? Is this fine now? This is what you talk about, right, Sharat Chandra? Right. So similarly, if we have resistance and inductance, if it is individual, write individual. Okay, only one term related. Right. So this is the second mesh. Right. Then about the third one. So this is the third one. Okay. And now you can do it, right? All of you. We don't have time. Okay.
Yes, sir.
And this, you can write this as this form. Okay. Node 1, node 2, node 3. So node 1 and node 3 shared elements are R3. But here C23 and R23 is R2 we got. So now extra term is what? L3. Okay. And the complete circuit is this. Okay. I told this already, you do it at home, and I'm wasting another 10 to 15 minutes. So V1 is I1, V2 is I2, V3 is I3, M1, M2, M3, L1, L2, L3, K1 1 by C1, 1 by C2, 3, B1 1 by R1, B2, R2, R3, and R2, 3. Okay. All right.
Yes, sir. Sir.
So all of you can do it, no?
Yes, sir.
All right. Right. So this is what analogous. And similarly, you can do it force current also, no?
Yes, sir.
Practice and then, be ready for the next classes. When it is given in the examination, don't say like, Okay, so sir, it is not taught in the class, so we don't know. No way. And I'm telling you, it is better you have, I think by this time, ebook of Benjamin Sikwo. Do one thing. Don't feel like you are so great or better. Second year you came and then like school. No, take the exercise problems of all the Kuo book, solve it on your own, keep it ready. That will help you if you are preparing for the GATE examination, or that will help you when you prepare for your IES examination. The notes, right? You write notes now in the class, and I'm not that much so fast. I'm not changing the slides. No, I'm going step by step only. Write the notes, and upon completion of the topic, take up the problems of Kuo book, solve it, and keep it ready. And if you are preparing for your civil services examination also, you can take your electronics and communication engineering as one particular subject. So at that time, definitely it will help you out. Okay, right? So don't neglect it, right? And it is only the thing is laziness. Beat the laziness by solving these problems, and these notes will help you out like anything when you prepare for your competitive examinations. All right. So now let us go ahead. Uh, Sometimes what happens is the physical systems. All of you listen very carefully. Sometimes um, the physical systems are represented in the form of a diagram called block diagram. Okay, so it is called a block diagram. So block diagram. There are two terms. One is block, another one is black. You heard about black diagram?
No, sir.
Right. Black diagram, transistor block diagram, two-port network. When you represent any electrical or electronic components, you can represent using two-port network. No. See, transistor is there. This transistor you represent using black diagram, right? Means here what is there inside you don't know. So you represent like black magic. So block diagram is internally, if you don't know what is that, then it is block. So this you represent using H parameters, right? This is the transistor, but the transistor we represent using black diagram. Two-port network. We don't know what is there inside. That is called magic. Right. So it is called black diagram. And the moment you analyze and then do everything, then you represent this using H parameters, right? Okay, so it is HIE and then something like HREVC, and then this is what you write, no?
Yes, sir.
It is called black. Now we are discussing about block. So when physical systems are complex systems, then it can be represented using block diagram. Any physical system, mechanical, electrical, electronics, okay, any physical systems, if they are what we say, right, complex, very complex systems, liquid level systems, tank, and then block diagrams. So when you try to see, this is what liquid level system. Okay, and then its equivalent block diagram, what it is represented is. Okay, so sometimes very complex systems are written in the form of block diagrams by considering cause and effect relationship. Okay, by considering cause and effect relationship, right? So I think how they are represented and all, or do you want me to explain, like, shall I take a physical system and then how it can be written in the form of block diagram? Shall I take up? If you are interested, I'll take up.
Yes, sir. Please, sir.
Yes, sir.
Yes, sir.
Okay, right. So now let me take a electromechanical system. Now you know electrical system. Now you know mechanical system. Right. So now let me take an example of electromechanical system, which is a motor. Right. So coming to the motor, yeah, coming to the motor, can you tell me the applications of motor?
In a well to draw out the water, pump out water, use a
Yeah.
motor.
Do you use, okay, that is, yeah, that is pumping of water. Yeah. Any other?
Motors in vehicles.
Mm-hmm. Do you use in your regular life, boys? Right. You use trimmer, right?
Yes, sir. Yes, sir.
So trimmer, there also, trimming of your beard. And then, do you have earlier CD drive?
Sir, hair dryer. Sir, hair dryer.
Yeah, yeah, yeah. And one more example, if you have your desktop, you will have your DVD writer, right?
Yes, sir.
Yes,
The
sir.
moment you press button, then the DVD will come out, no? Okay, so then all examples of uh, applications of motors. Okay. So there are so many applications. I have my own notes there somewhere else. Searching for it. It's not actually my PPT section. You will be having Give me 2 minutes. Give me just 2 minutes. Yeah. So now let us go ahead. Let me give you a brief introduction of motor because we are electronics students. So, I think in first year, anywhere the motor concepts are introduced. Anywhere?
Yes, sir. In PE.
Yeah. So now let me introduce this with the help of when you model it. So now I'm considering a motor. So now this model concepts, how we can try to understand. Now let me try to see. So magnet, a permanent magnet. So permanent magnet, when you take up this magnet, so then it will form magnetic field, and then the field lines are from north pole to south pole. That's what we say, right? So electromagnet is magnet that is created when electricity flows through a coil of wire, right? So now here, if you try to see, I'm taking a wire and then I'm winding it, and then the current enters at A and then leaves at B. Right. So the north pole is formed at the top, and then the south pole is formed at the bottom. The field lines are from north to south. So up to this point is clear, all of you? Right. So this is north and south. So if current is entering at B and leaving at A, so this is north and south. Right. So now I'm talking about electromagnet, and then now I'm introducing a nail in the wire. So if I connect the battery like this, the north pole is formed here and south pole will be formed here. So this point is clear now. Now this example to this example, what happens to the strength of magnetic field? Will be more here or more here? What is the use of this nail? We call it as core. Core means what? What is the use of core? Here it is air core. There is nothing like, here only air is the medium, right? But here now, let us take, I'm introducing an iron or iron nail. What happens to the magnetic field compared to this case? Oh God. Okay. Right. You heard about cores, air core, iron core, and then different cores in inductors. Okay. Right. So now what I'm trying to do, yeah, so the battery feeds current through the coil of wire, and then the current in the coil of wire produces magnetic field. Okay, as long as battery is connected. So if I want to reverse it, then what I do? If I want to reverse the poles, I simply reverse the battery. Right. Now, so the same setup I am keeping in a permanent magnet. Yeah. Jayant or anybody, without wasting time. Right. So this is what the battery, and I can take it as armature equivalent, and then this is the stator equivalent. Motor will be having your stator and rotor, right? So this is stator and this is rotor kind of thing. Okay. So the magnetic field lines are from north to south. Okay. Right. And here, due to this, the magnetic field lines are from north to south. Okay, right. So these two field lines are cut each other and produce a star. Correct? Yes or no? Absolute silence.
Yes, sir.
Yeah. So now, if I want to know the direction of movement of this rod, which is connected to the nail, which law I should use? Motor air, how electrical energy is converted into mechanical energy. This is what a motor. So this, here, see, this is like stator winding. If I can show you the cross section of motor. Can you see this now? Can you see the screen?
Yes, sir.
So here, this is what rotor, okay? And then this is what stator winding. So this stator winding can be, formed by using magnet, or also can be an electromagnet. Okay. So this is what this. Understood now? So this is equivalent of stator. Okay, this is equivalent of stator. Right. And then this is what the rotor which is moving. Okay. Right. So this two magnetic lines which touch each other, and we will be using what? Permanent. Which law we will use to know the movement of the rod?
Fleming's left-hand rule.
Fleming's left-hand rule. So instead of talking now, I can. Okay, instead of talking now, I have a video, I guess, somewhere around. It's a small, 2 minutes or 3 minutes of video by which you can understand very easily this particular concept. Yeah, so you just listen to this video. Just a second. This. Yeah. Listen to it.
Now we see that
Yeah. So this is what the working of DC motor. Okay. So now this is what we have to model. So which laws we have to use? Tell me. Which laws we have to use? Tell me. How the book. Okay, so you send me the ebook, right? So now, so this is what the DC motor, and then the cross-sectional area is, cross-sectional is this. So you have armature and then the field coil. Okay, so armature and the field coil, and this we can model by using, just a second. Yeah, so now let us, it's very easy for me now. Within 5 minutes, we'll be closing. Yeah, so this is what this is how the DC motor works. So now what we do is here, this is what the equivalent diagram is, what it is drawn. So RA here is the armature resistance of the, you have an armature winding, right? So armature winding is having resistance, that is RA. Armature inductance is what it is, LA. Okay, so this is what RA and LA. And when motor rotates in one direction, it produces back EMF. So that back EMF is represented with VB of T. Okay, and when you apply armature voltage here, that will be converted into torque. So the torque is given as Tm of T, and angular rotation is what it is given as Tm of T, right? And here this is what armature coil equivalent, and then this is what called stator, right? So stator here it can be fixed or it can be varied. It can be replaced with a permanent magnet. So this is electrical part, this is mechanical part, and the combination is what electromechanical part. So here IA is what armature current, RA is what armature resistance, EB of T is back EMF, TL of T is load torque, TM of T is motor torque, TM of T is rotor displacement, right? And LA is what armature inductance, A of T is applied voltage, KB is back EMF constant, Psi is what? Magnetic flux in the air gap, right? And Jm is what? Motor inertia. So this is what the equivalent one, right? So now we will make certain assumptions. The first assumption is the air gap flux is proportional to the field current. The air gap flux is what? Proportional to the field current. So this is what the field current is. Okay, so this is what field current. Here it is what? Armature current or armature voltage. So the air gap flux is proportional to the field current. Yes, correct. So psi is proportional to IF. So psi is equal to K1 IF. That is what assumption 1. Assumption 2. The torque developed on the motor shaft is proportional to the product of armature current and air gap flux. So tau is proportional to, that means you have field current and armature current. So which is tau is proportional to the product of psi and Ia. Psi is equal to K1 IF. So K1, K2, Ia, IF. Right. So this is what the second assumption we are making. So K1, K2 are constants. Now I can vary the torque by varying armature current or field current. So here in the case, then the motors are called armature control DC motor or field control DC motor, IF or IA, right? So now I am assuming IF constant because permanent magnet I am saying. So field current constant. So torque is proportional to IA. So I am mathematically modeling armature current control DC motor, right? So now the next assumption is the back EMF is proportional to the velocity of the motor shaft, correct? So VB is proportional to d by dt of theta m. So VB is equal to Km theta m. So now, right, so this is what the power. Now are you ready? What is the time now? What is the time now? It's very simple only. But what is your next period? Can I go ahead? So another 3 to 4 minutes. Or shall I explain it in the next class? A physical
Yes,
system is what we have to write in the form of block diagram is what the objective of the class. If you say like, yes, sir, 5 minutes, we can go ahead, means I can finish it up, or otherwise I'll be taking up in the next class.
Yes, sir, you can go ahead.
Sure. Varun? Varun? It is now exactly 10. Can I go ahead?
Yeah, next class.
What is your next class?
TLEW, sir.
So anyhow, you have to join for that class, no?
Yes, sir, exactly. It is at 10 o'clock.
Yeah. So I'll be discussing from this point in the next class. Okay. All right. Thank you.